Now, let's learn about algorithms by feeding horses. We have 13 apples and want to feed 5 horses. Because we don't have a knife, we can only feed whole apples. For reasons of fairness, every horse should get exactly the same number of apples. We start and feed each horse an apple. As we can see, we have enough apples left to feed each horse another apple. So we go on and feed each horse one more apple. Now we have only 3 apples left and have to stop feeding. This example was intentionally very specific, very concrete. Let's go on a little journey and train our ability to think and speak more abstract. Remember, abstract means that we describe facts in more general terms. Instead of saying we feed 13 apples to 5 horses, we could say feed n apples to m horses. Let me ask a question. Is it important for the understanding of the problem and its solution that it is about apples and horses? Or could it also be about bananas and elephants? If you love horses or love to eat apples, you might answer the question with yes. But from a technical point of view, it does not matter if we are talking about apples and horses or bananas and elephants. So we can describe the problem even more abstract. We want to feed n fruits to m animals. Let me ask a similar question to the one I just asked. Is it important for the understanding of the problem and its solution that it is about fruits and animals? Or could it also be about 50-cent coins that are distributed evenly across wallets? We can take abstraction to the extreme and say we want to distribute evenly a set of n equal pieces to m recipients. A recipient here can be an animal, a person, or even an object like a wallet. Now, we have a very abstract definition of our problem. But what about the solution? Let's go back to our concrete problem from the beginning and try to find a solution. We write down the instructions required to solve this problem. Instruction 1. If there are less than 5 apples left, stop feeding. Instruction 2. Feed 1 apple to each horse and continue with step 1. That's all we need to describe the solution of the concrete problem. Let's have a look how our instructions change if we get more abstract. Our first instruction asserts that there are enough apples to feed each horse 1 more apple. So far, we had 5 horses and therefore stopped feeding when we had less than 5 apples left. Now we have m horses, therefore we have to stop feeding if we have less than m apples left. The second instruction does not change. If we get more abstract, the logic of our instructions remains the same, but we have to generalize our wording. Instead of apples, we talk about fruits. Instead of horses, we talk about animals. If we take the abstraction to the extreme, the logic is still the same, but we have to generalize our wording again. Instead of fruits, we talk about pieces. Instead of feeding, we talk about distributing. And instead of horses, we talk about recipients. Now we have a very abstract solution that consists of generalized instructions. Our solution is not restricted to solve the problem feed 13 apples to 5 horses. It can solve all problems of the kind distribute evenly a set of equal pieces to recipients. What we have developed here is called an algorithm. An algorithm is a sequence of instructions that can solve a class of specific problems. The problem class we solved here is the even distribution of pieces to recipients. We often write a computer program that follows the instruction of an algorithm. We say that we implement an algorithm. We develop this algorithm only for didactic purposes. In practice, there are simpler methods to solve the problem class evenly distribute pieces to recipients.